Welcome to Transfer Phenomena in Bioprocessing NPTEL course, week 6, lecture 4. So, today we will be discussing about minimum bubbling velocity in fluidized-bed reactors. So, by end of the lectures, we will be able to learn. So, I will be explaining for here the operating limits of fluidized-bed reactors. What is that one? It is identifying the role of the minimum fluidization velocity. We use VMF, minimum fluidization velocity VMF, then terminal settling velocity VT or UT, and then the safe operating region for the stable reactor performance. So, we will be discussing today. Then what is the differentiate between a minimum fluidization velocity UMF, then minimum bubbling velocity UMB, B, right, bubbling velocity U of MB, minimum bubbling velocity. Then also to evaluate the factors governing the onset of bubble formation in the fluidized bed. Then finally, we apply the empirical correlation, then the hydrodynamic relationship to estimate there is a minimum fluidization velocity, bubbling velocity UMB, we call it UMB, minimum bubbling velocity. Then predict the bed expansion, there is a expansion be there when you increase the velocity of gas flow rate here. Then of course, we have to assess the influence of the particle, then what is the fluid properties on the fluidization behavior. So, the expansion of fluidized bed, operating limit of fluidized bed, what is operating limit here? So, we know already, we discussed the previous class, the fluidized bed operates efficiently within the specific range of fluid velocity. Otherwise, we cannot run with efficiently here. So, example, if the fluid velocity is very low, very low, then there is no fluidization cannot occur, we called as a fixed bed. So, conversely, if the velocity is too high, is a very high, then the particles are carried out the reactor. Whenever velocity high, then whatever the particle, it's come out from the reactor. So, definitely therefore, we have to operate the fluidized bed reactor with the two important operating limits. So, what are the limits here? There is a lower operating limit than the upper operating limit. So, the lower operating limit we called as a minimum fluidization velocity. We cannot run less than UMF value, because if you run, what will happen? It will act as a packed bed or fixed bed. So, then we cannot overrule of if we cannot increase the terminal settling velocity. So, what will happen if we increase the terminal settling velocity, then automatically whatever the particle will come out from the reactors. So, definitely we have to maintain the specific range of lower operating limit, upper operating limit in the fluidized bed reactor. So, the lower operating limit, that is called the minimum fluidization velocity. So, what is minimum fluidization velocity? The minimum fluidization velocity is the lowest the fluid velocity at which the upward drag force balance, that is balances the effective weight of particle, then there is a initiation to start the fluidization. To initiate the fluidization, that point is called as the minimum fluidization velocity. Then when the superficial velocity, if below the value, there is a minimum fluidization velocity below this value, and then the drag force is insufficient to suspend the particle. So, what will happen here, that whatever I discussed, if it go to minimum UMF is fine, but if you go to below the UMF value, then the particle remain fixed, there is no bed expansion occurring. So, then the reactor behaves a packed bed, not a fluidized bed. The reactor behaves a fixed bed, because the particles are fixed here. Then of course, if it fixed bed, then the mixing heat and mass transfer, of course, it is a very relatively limited compared to fluidized bed. So, what will happen if upper operating limit? For upper operating limit terminal settling velocity, we called as a UT. So, this is a fluid velocity at which the upward drag force become equal the gravitational settling forces acting on an individual particle. So, if it increase the ut, then there is a with the ut velocity, if we increase or equal to u, then automatically the particles no longer remain the fluidized bed, because when you increase the velocity, it goes like up to terminal settling velocity, it behave as a fluidized bed. If you increase the terminal settling velocity, then it behave as a not fluidized bed, it is no longer fluidized bed. That is only we are saying that if it increase, what will happen. So, then instead of that one, that what will happen, that one, if you increase the velocity, then definitely they are lifted by the fluid stream, and then whatever the particle will come out, carried out the reactors. So, this phenomena is called as a particle entrainment. So, whenever the particle coming outside, that is called a particle entrainment. So, what is the safe operating region? If somebody asks what is the safe operating region, it should be a stable and an efficient fluidization. So, the reactor should operate between the UMF to UT. The velocity here is, if you want to fluidize bed and then you want to control with the fluidized bed, you should act with the UMF to UT range, not less than. If you go to less than, it behaves as a fixed bed or packed bed. If we above, then automatically the particle whatever this one will carry out the from the reactors. So, that is the reason we have to operate the within this range for to the safe operating for the fluidized bed. So, within this range, definitely the particle remains suspended, because it is working in the fluidized bed, it should be a suspended, and then good mixing also achieved. We will get a very good mixing achieved here. Of course, heat and mass transfer also enhanced here. Heat and mass transfer gets enhanced. There is no particle loss in the minimized here, because it is working in the proper operating conditions, the safe operating regions. So, what is the safe operating region range? So, if you assume for fine particle, this is called Reynolds number fluidization. Reynolds number, we write d UMF dV rho by mu, we write like this. Okay. So, this is a Reynolds number fluidization, it is a less than 0.4. So, then the V dash by VMF equal to 90 times. So, you want to run the safe operating here, the maximum operating velocity, the fine particle, that is very important. The fine particle is roughly for 90 times of minimum fluidization velocity. So, if you take a coarse particle, like a large particle, then the Reynolds number fluidization should be a greater than 1000. So, in that case what will happen, that maximum operating velocity is a roughly 9 times of minimum fluidization velocity. So, that is the safe operating range of this one. So, what will happen if a large particle have a much narrower operating range than the fine particle, no, the fine particle have low settling velocity, the velocity is low, then there is a large surface area. If a fine particle is there, automatically the surface area will be very very high compared to large particle. Then also the stable expansion, but whereas the large particle whenever there, it is a heavy, of course the inertial forces definitely dominate, then entrainment occurs very soon. So, then we need a correct prediction of bed expansion is essential to the effect here. So, what are the things here? The reactor height, because this will definitely affect the following things: reactor height, then the distributed design, residence time, there is a pressure drop, then oxygen transfer, biomass retention and mixing efficiency. So, then we need a correct prediction of the bed expansion is very important, otherwise it will affect for all type of whatever below mentioned the parameters or variable. So, we have to study the prediction of expansion. So, for what are the equation we used here, the expansion of the fluidized bed, this we already studied, V dash equal to K1 of for the fluidization velocity, the epsilon 3 by 1 minus epsilon here. If it expand the height, bed height, I want to measure the how much the length expanded with different porosity, then we should use the L equal to L naught, this one. So, if it fine particle, then the maximum velocity equal to 90 times of the minimum fluidization velocity. So, in case if a large particle if you use, then the velocity here is a 9 times of a minimum fluidization velocity. These are the equation we will use for this fluidized bed reactors. So, what key takeaway we want here, the bed expansion definitely occurs once the minimum fluidization because of due to increased fluid drag. If Reynolds number of fluidization REF, we write REF the Reynolds number fluidization. In the laminar term, because it is a less than 20, we call it as a laminar term. The laminar term of ergon equation dominates if it less than 20. If greater than 20, then automatically it is a turbulent flow, then inertial force will dominate. So, the leading to bed, then the expansional relationship we already studied V dash equal to K1 of epsilon 3 by 1 minus epsilon. So, what will happen if you increase the superficial velocity, then of course, the porosity and the bed height also it non-linear get increases. It is not a linearly, it goes like non-linear behavior when you increase the superficial velocity. So, the expanded bed height follows this, we already know that L equal to L naught 1 minus of epsilon naught by 1 minus epsilon. We will use this relation to find the how much expand the length of the bed. So, definitely the fluidized bed must operate between the minimum fluidization velocity than an entrainment limit. So, we have to predict properly the bed expansion because the fundamental designing of fluidized bed bioreactor, then say example for immobilized enzyme systems, some adsorption, bioabsorption packed bed column, there is a wastewater treatment reactors are there. So, here we have to properly predict that one, then only we will get a good efficiency of most answer, then the stable hydrodynamics are very essential for here. So, now we will discuss about the minimum bubbling velocity in fluidized bed. Previously we discussed minimum fluidization velocity, but here minimum bubbling velocity. So, what is the bubbling velocity here? After completing this one, we will be able to learn what is the transition between the particulate fluidization velocity to bubbling fluidization. Then of course, we will learn minimum bubbling velocity, what is the definition of that one. So, what is the difference between minimum fluidization velocity than minimum bubbling velocity? We should know what is the difference between these two also. Then of course, if you know that one, then we have to calculate the minimum bubbling velocity. There is a empirical correlation there, we have to use that one. Then finally, the importance of bubbling in industrial bioreactor. What will happen if the bubbling here? So, after packed bed reaches the minimum fluidization velocity, we call it as a VMF. The VMF is the minimum fluidization velocity. The particle becomes suspended and it will upward to the flowing of the fluids, that is called minimum fluidization velocity. But however, the fluidization does not always immediately produce gas bubble, because why? Because again they depend on the particle properties. Some beds expand uniformly, some beds will not non-uniformly. So, definitely the particle property depend on the bed expand uniformly. So, then some others immediately form bubbles, some type of reactors fluidization here. So, some remain like homogeneous certain times and short range, then immediately the before bubbling starts here. So, definitely then the velocity at which the first stable gas bubble appears is called as the minimum bubbling velocity. So, there is a stable gas bubble, the first bubble appear that we call as a minimum bubbling velocity. So, the minimum bubbling velocity defined as the superficial velocity at which the first stable gas bubbles are observed within the fluidized bed. So, we always write VMB minimum bubbling velocity, this one velocity, the units are meter per second, same units what we are using the other velocity here. At velocity below, what will happen? Below VMB, the particle remain uniformly suspended and of course, gas flows uniformly through voids, the minimum bubbling velocity below. But what will happen if you use above minimum bubbling velocity, then definitely there is a gas no longer distributes uniformly. Of course, is excess gas form also bubbles and then bubble rise through the bed. So, this marks the beginning of the what is the bubbling fluidization here. So, what is the difference between minimum fluidization velocity than minimum bubbling velocity? What is the difference this one? So, if you take a minimum fluidization velocity, the beginning of particle, the suspension here, and but the bubbling, the beginning of bubble formation here. So, there is a pressure drops equal the bed height, bed weight, the pressure drop equals to the bed weight, but here the excess gas form bubbles here. So, entire bed get fluidized for this one. If it minimum fluidization velocity, for minimum bubbling velocity, the gas begin bypassing to the solids through that one. So, we write here simple VMF, and but here we write V of MB. Minimum fluidization we write VMB. So, then if you want to calculate the empirical correlation for minimum bubbling velocity, there is a calculation here VMB equal to 33 dP by mu by rho minus 0.1. So, this is the empirical correlation to find the minimum bubbling velocity. So, what it stands here VMB, we know that one minimum bubbling velocity, that is a meter per second, then dP is the particle diameters, then what is the gas viscosity, then gas density in terms of kg per meter cube, then Pascal seconds. So, what will happen now, the effect of the particle diameter, now we have to discuss one by one. So, what will happen the minimum fluidization velocity if particle diameter is this one, then what will happen if viscosity, so what will happen if gas density. So, the larger particle whenever the possess greater mass and inertia, because inertia also more and mass also more, but consequently the higher gas velocity is required to, because we need higher gas velocity required to lift the and separate the particle sufficiently for bubble formation. This is the effect of particle diameter. Then if the effect of gas density, what will happen here, a gas which a higher density, it exerts larger drag force on the particle at the same as the superficial velocity. So, what will happen as a result here, the particle become fluidized more easily, and of course, the gas bubble begin to form at a lower velocity. Same way for gas viscosity figure is what will happen. If gas viscosity determines viscosity, because viscosity determines the resistance to the flow, and of course, what is the influence of the moment and transfer between the gas and solid particle. So, example, more viscous gas, what will happen? The more viscous gas is there, it definitely resists the motion, because viscosity more, it resists the motion, and definitely the dissipates energy more effectively than the delaying the formation and the growth of the stable gas bubbles. So, now we discuss three: gas viscosity, then gas density, then particle diameter, how the affect the minimum fluidization velocity here VMB. So, that only we discussed using the empirical correlation. So, now we want to design the bubbling fluidized bed here, then we should know what is the minimum fluidization velocity, then minimum bubbling velocity. So, the velocity at which particle just get behind fluidized, that we call as a minimum fluidization velocity, but same way the velocity at which first stable gas bubble, that is very important, the stable gas bubble appears, we called as a minimum bubbling velocity in the fluidized bed. So, definitely we have to compare both velocities, then we will get some idea about what conditions works here. If somebody asks whether the fluidization velocity lower than the minimum fluidization bubbling velocity, no, because the minimum fluidization velocity, the bubbling velocity always should be a higher compared to minimum fluidization velocity, because the VMB is always higher value compared to the VMF value, because bubbling velocity should be higher than the minimum, otherwise it is totally wrong. Otherwise sometime some design purpose it may be equal also, but not in the less than of minimum fluidization velocity. Okay, that is very important for here. So, that is the message I want to give here. The minimum bubbling velocity always higher than the minimum flotation velocity. So, what key takeaway? We discussed about the what is the minimum bubbling velocity, and we always write VMB, that is a meter per second. Of course, the bubble formation significantly influence the mass transfer, mixing, and then reactor performance. So, then we of course empirical correlation, at least we discussed, it provides the practical estimate of the reactor designs. So, problem 1 we will discuss the packed bed bioreactor, the packed bioreactor containing immobilized enzyme carrier. So, there is a particle used to fluidized using air at 30 degree and 2.5 atmospheric pressure. The pressure is the 2.5 atmospheric pressure, the absolute pressure. So, then the property of air, because we already discussed 30 degree, same 30 degree, the 2.5 atmosphere, there is a viscosity value is the in terms of 1.87 into 10 power minus 5 Pascal per second. Then there is a density is there, density is the 2.97 kg per meter cube. So, then there is a gravity, that is G equal to 9.81 meter per second square. So, then we have to determine the following properties. The following we have to determine the particle possesses the following properties. These are properties. So, we have to determine first minimum fluidized-bed height. They are asking minimum fluidized-bed height, then the delta pressure drop. What is the pressure drop? Then the minimum fluidization velocity UMF, then maximum allowable fluidization velocity UT, then voidage when operating at 2.5 times of the minimum fluidization velocity, what will happen here. So, then finally, they are asking minimum bubbling velocity. So, whatever we discussed, we just put up the problem according to that one. So, there is a particle diameter 0.15 millimeter, that we have to convert in terms of meter. Then the sphericity, since it's a sphere, it is a non-uniform particle. So, then we always write as 0.90. So, there is problem is already given. Then particle density, there is a particle density, then there is a gas density, many things are there. Particle density 1050 kg per meter cube. Then there is a voidage of minimum fluidation, that is the 0.45. Then what is the mass of the particle, that is the 350 kg. Then the cross sectional area of the packed bed bioreactor, that is a 0.35 meter square. So, using this we have to find it, these are determined this one. So, same thing, particle diameter we convert in terms of SI units. Then there is a particle density is there, we called rho P, the gas rho G, gas density, viscosity mu, then the sphericity, voidage, then reactor area is there, then particle mass, then gravity. So, first what we have to do, we have to find what is the minimum fluidized-bed height, then pressure drop, and then what is the minimum fluidization velocity, then what is the maximum, that one allowable velocity UT, terminal settling velocity. If you 2.5 times if increase, what will happen, then finally minimum bubbling velocity here. So, then volume of this one solids, we always write V equal to M by rho. Rho mass of solids we know 350 kg, then the density of particle, we got volume of solids 0.33 meter cube. If height completely occupied by the solids, then there is no void space, then we write as a porosity is a 0. If porosity is 0, then L1 equal to Vs by A, L1 equal to Vs by A. So, area of already we know area of the reactor, then the volume of force we know volume of solids, then we got 0.952, the height of that one we got 0.952. So, now we have to get the length of that one. Minimum fluidized-bed height, this formula we know already we discussed here, L1 by LMF equal to 1 minus of this one. So, the epsilon 1 0, because there is no void space, but minimum fluid velocity we know 0.45. So, then we got 0.55 here, then we do not know LMF value, then L1 we got from here, the L1 here we got from here. So from there we can get it, from here we can get it minimum fluidation velocity, minimum fluidation, the length, how much the bed height, minimum fluidized bed height through LMF we can calculate how much in terms of meter. So 1.73 meter. So pressure drop, we know pressure drop delta P equal to, we know that one LMF by 1 minus of x log mf rho P minus rho G into G. So we know 1.731 from previous this one, then 1 minus of, we know minimum fluidation velocity 0.45, then the density of particle here, the density of gas, we get from here the pressure drop at minimum fluidization. What is the pressure drop? The delta P equal to 9.78 kilopascal, minimum pressure drop at a minimum fluidation. So we have to calculate of the minimum fluidation velocity Vmf here. So that's the Ergun equation here. We already know that Ergun equation we know, but we are everything in terms of put minimum fluidation velocity, minimum fluidation porosity, like that. So NRE, the Reynolds number also minimum fluidation here. So then 150 here, same way modified here, and after modification the Ergun equation already available and we are modified based on that minimum fluidation velocity. There is a NRE, we write NRE minimum fluidation here, where NRE minimum fluidation, then velocity also we have to use a minimum fluidation velocity. So there is a density, then dP by mu. So it look like now quadratic equation, because we know what is the value of this one, same way here and same way here. So after solving we got this one. It look like ax square plus bx plus c equal to 0. So same way we have solved here, we know what is the a value, a here, everything at a capital, you same thing you can use it here, a equal to this one, then the b equal to here, then c equal to here. You can use, if you want to calculate the x value here, x equal to NRE, NRE minimum fluidation. So we can write minus of b plus or minus root of b square minus 4ac by 2a. You want to find the what is the root of that one. So you see the quadratic equation, you substitute the value, then you get the Reynolds number. There is a two Reynolds number will come, one is a positive, other one is negative. Negative number is not at all possible, the Reynolds number. So we have to take, we should take only positive value, that's the Reynolds number is a 0.262. So once we know Reynolds number and we know the this equation, Reynolds number equal to diameter of particle, minimum fluidation velocity, density, then viscosity. So rearrange the equation, then get the minimum fluidation velocity Vmf equal to 0.01, Vmf equal to 0.0110 meter per second. So from there we got it the minimum fluidation velocity. So now we need what is the maximum allowable, because if Reynolds number is, we already discussed, if Reynolds number is less than that value, but we got here 0.262, so then automatically it falls in the first one. So Vt by Vmf is 90 times of approximately here. So Vmf we know, and then we can operate the safe operating that one maximum allowable fluidation velocity, the 0.99 meter per second. We should not cross this one. So the expansion of fluidized bed, now we already, this problem itself we discussed, if it 2.5 times, if it expanded, what will happen? The problem first is still given, the V new velocity equal to the 2.5 m of Vmf. So Vmf we already know, then we got the new velocity, what is the velocity of that one? So we got new velocity, but we expanded here 2.5 times of the problem itself given, then only we are multiplying here. So new velocity we know, then we can calculate using, we know what is the minimum fluidation velocity, because the previous problem we got 0.011 Vmf here. Then from there we know minimum fluidation velocity 0.45, then get the value of K1. So once K1 you know, the K1 you can substitute, but the new operating velocity, because the new operating velocity 2.5 times of, okay, the first one is for as it is that one, but the new operating velocity is the 0.0275, because they mentioned 2.5 times of increase what will happen. So new velocity, then again you have to use new velocity, then you go for trial and error procedure, and we got the porosity equal to 0.57, that is the porosity of that one. So, once porosity done, then we know minimum bubbling velocity 33 dp is the diameter of particle, then mu is the viscosity, then rho g is the density, gas density. Gas density already problem given, viscosity also already is there, then diameter of particle in terms of meter, we are calculating this one. So, finally, we got the minimum bubbling velocity. So, you can see here the minimum bubbling velocity is always higher than compared to the minimum fluidization velocity. Then only it cannot be a less than minimum fluidization velocity, that is sure. So, then minimum fluidized bed height we got that one, then pressure drop we use the pressure drop delta P equal to, we use the 1 minus of x log mf, like okay, that equation we use here. Then what is the allowable velocity, that is the ratio 90 times of that one. So, how much we can use the terminal settling velocity. So, voidage after expansion, once if we expand 2.5 times, so what will happen here, that is a 0.57. So, then minimum bubbling velocity using this equation we got in. Thank you.